Hey, this is Dre, and this is a screencast about traffic shaping with pfSense. That's the agenda. So pfSense is a FreeBSD distribution that is purpose-built as a network utility appliance, which basically means it's FreeBSD with some sugar on top that comes in the form of configuration templates and service configurations and administration tools that allow this to be quickly deployed and configured for the use of kind of a network utility device like a router or a firewall. So we use this in order to get all those typical services like DHCP and NAT. Also, we want accountability for what's happening on the network, and we want the ability to see like where the resources are going. So there's lots of logs and graphs that you can use to learn about usage patterns and see what's going on. And there's also a bunch of extra packages and things you can install to add value. VPN services, DNS caches, various kinds of proxies, all kinds of NAT traversal protocols are implemented here, dynamic DNS clients, and lots of other stuff. There's like a package layer for pfSense that kind of sits on top of the FreeBSD ports tree and sort of integrates with the pfSense administration tools. But the main reason for me is to do traffic shaping. So traffic shaping is a way to solve the problem that is created when you have competing use cases on a network that is not fast enough to do what everyone wants all the time, such as pretty much every home internet connection. So the two use cases are, on the one hand, you have bulk traffic, such as iTunes downloads or YouTube uploads. And on the other hand, you have interactive traffic, such as online games or any kind of network-based audio or video conferencing, or let's say SSH sessions, where you're doing interactive command line stuff where latency is very important. The problem is that the bulk traffic will, by design, try and soak up all of the available bandwidth, which means that the interactive traffic now is suffering from that because there's higher latency because now you have congestion at the edge of the network, which is your internet connection. So we want to keep the interactive things quick by minimizing latency, but we also want to allow the bulk traffic to run at high speeds, so we can sort of get the best of both worlds. We don't want to just apply artificial limits. We want to do things in a smart way. So that's kind of the goal state. But before we get there, we got to get this thing up and running. So for hardware, I chose the Socrus 5501, which has Ethernet ports and 512 megs of RAM and a CPU that's like sort of fast, internal CF card slot. Also some serial stuff, but we're not going to need that. So you download a release image that is suited for the size of the CF card that you have and also for the architecture that you have. In my case, I chose the 4 gig i386 NanoBSD image, and this image is a device image that includes all of the partitions of an installed FreeBSD system. So you just drop this image onto your CF device. You have to have a CF card reader, of course, so on your computer. So you drop the image onto the CF device, and then you pop the card into the Socrus and you boot it, and that's totally it. There's no installation. The installation was done by the people who made the disk image. You're just applying this disk image to the CF card. So then you plug a computer into the LAN port, which in the case of the Socrus is the first Ethernet port, and that computer pulls a DHCP lease. And at that point, you can use the web administration tool to walk through the initial setup, which I'll show you now. So this is the setup wizard, and it's going to walk you through the initial setup of your pfSense device. So many of these values are pre-filled in my case because I've already been through the setup wizard a couple times. So you can set a host name and a search domain if you want. You can either specify DNS servers and or allow those to be overridden by what is provided from DHCP on your WAN port or ports. You can set a time server, and that's so that FreeBSD can keep its clock in sync. And you can set how your WAN port is configured. Typically you want to use DHCP, and we were using a different device, and the cable modem didn't want to give me a lease because it's Comcastic, so I'm just spoofing the MAC address of the previous device, and that works. So there might be various other IP configuration stuff that you need to fill out. If you know that you need to do that, do that. And you can also block traffic from networks that should never be entering your network, such as reserved networks and that sort of thing. You set the LAN IP for your device. You can set an admin password, which I would highly recommend. This is also used as your SSH password. And then you click reload. It applies the configuration. And then you get dropped back to the, I'm not going to do this of course because I've already set up my device. You get dropped to the dashboard. Now the dashboard is configurable. You can add any of these little widgets here or remove them by closing the checkbox. But I just like my dashboard with just this gateway widget here, which is sort of pinging my default gateway every, little while and showing me the status. So some of the next steps that you'll probably take are to set up the DHCP server, specify DHCP range, and maybe do some static maps. And you probably also want to do NAT. So under firewall, you want to make sure that NAT is enabled. And I believe that's pretty much all set up for you by default. There's not even a NAT configurator here. It's on. Next, let's take a brief look at some of the monitoring tools available via the web administration tool. And these come in the form of logs and graphs. So we'll start with logs by choosing System Logs from the status menu. And the first one we see in this list of tabs here is the system log, which shows you kind of top-level pfSense events like config file reloads, service starts, service stops, logins, that kind of thing. The firewall tab is going to tell you about network traffic. For example, you can see all the crap that's bouncing off your WAN port if you have a connectable IP address from the internet. There's also a summary view that breaks down activity into various ways of sort of presenting it, so you can see kind of a high-level view of top talkers on your network, source IP, destination IP. It's kind of a interesting way to get a high-level view of network activity. There's also various things available under the diagnostics menu. For example, you can see your ARP tables, see what devices are on your Ethernet networks. You can look at all the states, the current network states that are active through your network, and individually close them if you want by clicking the X on the right, or you can flush them all by using the Reset States tab. There's also a system activity view, which is really just the top command line tool, and we'll talk more about command line tools in a second. So next, let's look at some of the graphs. So if we choose RRD graphs from the status menu, we'll see a series of tabs here which represent different graph views. So the one that I set as my default is the quality graph. So this is based on ping information to your default gateway on any of your WAN interfaces. So this represents the minimum network latency that any of your traffic will experience. So our goal with traffic shaping is to keep this as flat and low as possible. We can see a graph of just sort of packets in and out, which is sort of one way of viewing network activity. We can also look at CPU activity on the device. And all these graphs, by the way, go all the way out to 4 years. So it's really kind of set up for a very long-term resource monitoring and capacity planning, that sort of stuff. One of my favorites is the states graph. And this is basically counting up all the items that we saw in that previous states view, log view. So this sort of represents, how much network activity is going on, not necessarily throughputs or packet rate, but how many different things are going on, how many network state changes are happening. And there's also like a memory graph and one additional throughput graph, which kind of plots the in and outbound on different sides of the zero line. So that's what you can do from the web admin. There's other stuff to click around in, but that just gets you started there. Let's take a look at SSH. Now for SSH to work, you do have to actually enable that first under System General Setup, System Advanced, because it's pretty advanced. And then down here you toggle the Enable Secure Cell checkbox, and the password that you set as the web admin password is the SSH password for the root user. So We will log in as root once it picks up the phone. And when you log in, you will be presented with this pretty little menu, this little shell menu, which I think is pretty cute. And so it gives you a little bit of information about your network and gives you some sort of scripts or links to certain commands that you can execute. In my case, I'm just going to go straight for a shell. And now this is, as I said, FreeBSD. So, we can just run FreeBSD commands that we know to explore the system and see what's going on. One really nice administration tool is called pfTop. And pfTop has a bunch of different views, so you can use the left and right arrow keys to cycle through the different views. And in fact, many of these views have more information than will fit on a small terminal, so kind of want to make it wider to see what's going on. And so in any of these views, you can hit the type question mark to get like a little help display. So for example, if I want this to refresh more quickly, I can type S and then hit 1, enter, and now it's refreshing every second. If I want to sort these by the rate, I can hit capital R, and now they're sorted by rate, which is this column over here. So I can see, just what transfers are going right now. Or perhaps I want to sort by age and see what the oldest connections are on my network. Or can hit capital A again to sort by to reverse the sort. So I can see every new flow as it happens on my network, which is pretty nifty, I think. So there's lots of other commands that you can run once you have this root shell going, which I will not bore you with. So there's also the ability to do SNMP on the device, and to do that you go to Services menu, SNMP, and it shows the community name, which I think is great, which is supposed to be, like a password. Don't forget this little checkbox over here to enable it. So SNMP allows your device to, it's a service that allows connections from other devices on the network, and it will provide information about itself to the device that's asking. So for example, we can use a little program for macOS 10 called Examinet. And in the Examinet preferences, you just type in your SNMP community info, and then it will list the network interfaces on the device. You choose the one that you want, and now I have like a little traffic graph in my menu bar. And that graph is, being drawn from information that is coming from my Socrus device, my pfSense device. So every some interval, I send an SNMP packet query to the device and say, how much traffic is on your interface right now? How much have you transferred in the last n seconds? Actually, it's probably just getting the absolute values and then doing the time stuff. Anyway, you get a nice little graph. So there's a variety of SNMP tools you can use to do that. And then finally, I want to show you a package that you can use called ppflowd. So you would go into the available packages tab, find ppflowd, and then install it. And then once you do that, you'll have another menu under the Services menu. And this allows you to export NetFlow information from the device. So if you know what NetFlow is, it's just kind of a way of concisely representing network activity in a way that is very scalable at even very high bit rates. So there's sort of two parts to a NetFlow workflow, at least two parts. You have the NetFlow emitter, the thing that produces the NetFlow data from the actual traffic that's being observed, and that's what this ppflowd is. And then you have a NetFlow collector, and the collector is what receives the information and then perhaps visualizes it somehow. So in the case of macOS 10, there is a little collector called FlowStats, and I'll start FlowStats here, and after a couple seconds it should start receiving NetFlow data. Theoretically, it should start receiving NetFlow data. Come on now. You are enabled, right? Yeah, there we go. I guess it's a few seconds between updates. So this is a pretty bare bones NetFlow collector. it really doesn't do a whole lot of stuff. It just kind of shows you the last 1,000 bytes, last 1,000 flows sorted by bytes, so you can see your biggest transfer and then your top talkers and receivers. Pretty basic, but these get very, very fancy and very, very expensive. Do note, of course, that ppflowd is not maintaining any sort of history. This is just sending NetFlow packets, and anyone who wants to store this data for historical analysis has to do that on their end. So that's how you can set up various monitoring tools. Okay, now let's get to the point and talk about traffic shaping. So we're trying to accomplish a few different things. We're trying to keep latencies low as possible. And we're trying to make sure that throughput is as high as possible. Now, obviously, something's got to give because there's going to be congestion. So when there is congestion, we want to try to enforce a fair sharing of the resources across the various competing traffic types. So there's a lot of people on the internet who will tell you that queuing is bad. And in general, they're not wrong. The thing is that TCP is kind of designed to use packet loss as a way of determining how fast it should be going. But there's a lot of network devices out there that seem to be designed without this sort of concept in mind. So they'll try to buffer packets instead of dropping them. And the problem is sort of summarized by the term buffer bloat, where if you sort of amplify all these buffers across the entire path of many disparate links, you basically end up with a lot more buffering than is needed. And that ultimately allows TCP to not do its job as well as it could if you were to, let's say, drop packets more aggressively. So buffering or queuing typically happens at network bottlenecks. Now, traffic shaping does require that we do some queuing in order to accomplish the goals that we're setting out to accomplish. But we do definitely want to minimize the amount of queuing that we do, and we only want to do as much queuing as we need to actually get the job done. So to illustrate the problem a little bit, here is a graph of network latency to my gateway while I'm running a speed test from the speedtest.net website. And basically each of these graph samples is 5 samples per second. So every 200 milliseconds I'm sending a ping and I'm getting the time back. And on the right hand side you see sort of a view of interface throughput produced by the command line tool called pfStat, which is actually running on my Mac, not on the BSD and not on the pfSense device. Although you could install it there if you wanted to. So the point here is the scale here on this graph goes all the way up to 250 milliseconds. So normally, I have about 10 to 12 milliseconds of latency between me and my gateway. So I do this speed test run, and the latency spikes up quite high. And in fact, there are even some packet drops in there which are not represented on this graph. So that's bad. So if you're trying to frag some people or kill a boss or something, and this happens to you, you will notice. So in case you're wondering where that fancy graph came from, I made it with GNU plot. So what I'm doing is I'm sending a ping every 0.2 seconds to my default gateway, and then I'm filtering out lines that have the word ping in them, which is the first line that's emitted, and any ping timeouts as well. And then I'm running that through sed to extract just the numerical latency value, which is after the time equals string, and I'm putting that into a file called ping.dat. And then in another terminal window, I'm basically looping over that file and just pulling off the last 150 lines and passing that to GNU plot. And I have a little tiny GNU plot script that just sets the terminal size, and it's using a plot command with the dash as the input, which is standard input. And then every second, it's basically just rerunning that GNU plot command with the most recent 150 lines from that file. So you get sort of like a scrolling view. It's pretty neat. So to back up a little bit, you want to measure your throughput and your latency before you add any traffic shaping stuff. So this sort of gives you the baseline. So then you enable traffic shaping, and I'll give you some sort of demos of walking through the wizard to do this. But basically, you're going to want to queue uploads on your LAN interface, since that's the interface before the congestion part. Basically, that's where the congestion would occur. And then queue downloads on your WAN interface if you want to. And the reason that you have to measure first is because you need to set the queue limits to be a little bit less than the actual observed traffic rates that you achieve. And this is to make sure that the queuing occurs in the pfSense device and not on somebody else's equipment where we can't control it. So you're going to want to practice with the wizard. And as I said, I'll run you through an example of that. You're going to want to look at the results that come out. So you're going to want to look at the floating firewall rules that are created to match any sort of application-specific traffic that you may have defined. And you're going to want to look at the queues that are created by the system based on your inputs in the wizard. And you also want to remember that any changes that you make you want to make sure to do those changes with the web admin tool, because that means you can back up and restore the entire configuration. Don't try to manually inject rules from the command line with pf. I think you can do pretty much everything you need to do from the web admin, and it's a good idea to do that. So play around with the configuration. For my purposes, I want to match the Comcast speed boost nonlinear service curve. In order to do that, you actually have to create a 3-tier hierarchical queue. Now the wizard is only going to set up 2-tier queues, so you need to go in and create nested queues, and I'll demo that for you. But basically this is what my queue ends up looking like, my set of queues. You can see that I have one for the upstream and one for downstream as well. Priority is actually not used by HFSC queues. It's used by other queuing algorithms. But the key point here is, yeah, we're defining several queues and they each have different bandwidths, and that's kind of like the minimum guaranteed bandwidth. But the main money shot here is this upper limit curve, and we're specifying 3 values here. And basically, we have a burst rate, we have a burst time, and then we have a long-term rate. So basically what this means is, for any traffic that gets thrown into this queue, it's going to be allowed to burst at 3.9 megabits for 20,000 milliseconds or 20 seconds, and then it's going to get brought back down to 1.9 megabits indefinitely. So that's kind of like the behavior of the Comcast speed boost. And for reasons that I'm not sure about, this actually has the same leaky bucket behavior as the Comcast speed boost itself. Perhaps it's actually the same algorithm under the hood. And what that means is it remembers how much data you've transferred lately. So for example, if I burst for 10 seconds and then stop transferring for 5 seconds and then start bursting again, I'm only going to get 15 seconds of burst, not the full 20, because that first 5 seconds of burst still hasn't drained out of the bucket yet, if that makes any sense. Just read up on the leaky bucket. It's kind of like the inverse of that, but that's the idea. And so how do you come up with these values? Well, you come up with the values by measuring your connection before you start traffic shaping, and figure out how long it takes for your uploads and your downloads to fall from the speed boost rate down to the sort of sustained rate, and basically just keep iterating until you find values that work. So for example, after applying the traffic shaping rules, the same speedtest.net test run has the following results. The latency, as you can see, is much more tightly clustered. The scale in this case only goes up to 35 milliseconds as compared to in the hundreds last time. And perhaps even more important than that is that it's a nice tight cluster. We don't have any weird ramps or shelves or anything like that. And then on the right you see the throughput. Now throughput is less. There are in fact more lines here to represent all this test activity, which means it took a little longer. That's because we're not getting quite as much down and not getting quite as much up. We're curtailing it just a bit, 5 or 10%, just to make sure that we're doing the queuing in the pfSense device, and so that we can control exactly how that queuing happens and which traffic gets prioritized. So to make sure that you're doing the queuing, you can use pftop and hit left arrow once after you launch it, and that brings you to the queue view. And the column that I want to highlight here is the queue length column. And you basically just want to make sure that this number is non-zero anytime that you would otherwise be saturating your upload or download. So whenever you do big uploads, for example, you should see the upload queues getting packets. If you're never getting any packets in your queues, then that means the queuing is happening someplace else, and you are actually not having any effect with your queuing strategy, because perhaps the bandwidth limit is set too high on your queue, so it's never being limited. And so once you think you've got it all worked out and your latency seems low, just try turning on iCloud backup on all your iOS devices, and then like gigabytes of data will just fly up into the cloud. And if nobody gets mad, then hey, congratulations, it probably worked. So here's a couple of links about PF and HFSC, hierarchical fair service curve, which is pretty cool stuff. I would encourage you to read about it if it's interesting. So that's the end of the slides, and I do want to show you just some quick demos of how you would actually configure the traffic shaping as well. Okay, so just to demonstrate some of the stuff that I talked about, let's take a look at the traffic shaper section under the firewall menu. So you can look at your queues in a variety of ways. This sort of presents a hierarchical view of any of the queues that you have. And as you can see, I have a 3-tier hierarchy. You can also look at it sort of a flat list of the individual queues if you want. The limiter section is something that I am not using. This is basically a front end for the IPFW DummyNet, which is a entirely different way to do traffic limiting. In general, I would not recommend using this unless you want to actually just prevent or provide sort of flat artificial limits on traffic. I think a smarter algorithm that can actually borrow and use up available resources is better, and that's what we're concentrating on here. But when you first start, you're not really going to have much here. It's going to be empty, so you can use the wizard, another wizard, to help you construct a set of rules. And I'm going to walk you through one of the wizards here just to sort of show you some of the options. So we're going to pick the single LAN multi-WAN, which is also the one that you would use if you only have a single WAN as well. So we'll click that, and the first question we get is, hey, how many WAN connections do you have? We have 1. So next, it's going to ask us what queuing discipline we want to use. We want HFSC, which supports the nonlinear service curve, which is basically how we get the curve fitting to the Comcast speed boost. We choose our WAN interface. That was the schedule for the LAN and also for the WAN. And we can set some bandwidth upper limits here if we want it as well, which you should do based on the maximum burst rate of your connection. And in fact, I probably should have that up to 25 instead of 20. So for voice over IP, if you're using voice over IP, this allows you to create some special rules to prioritize voice over IP traffic, which I do not use. And there's also this thing called the penalty box, which is like, hey, someone's been stupid or whatever. Put them in the penalty box, not using it. And it can also create rules specifically for various peer-to-peer networking software. And this is a great way to curtail that sort of activity if that is your task, which it is not in my case. Aha, network games. This is more interesting. This will allow us to create specific rules that match traffic for various games. And notice, by the way, that I had to toggle this checkbox when I first got in here in order to actually light these values up. That's a problem that only happens if you rerun the wizard. So you can select the games that you want, and basically these are just templates for, specific source and destination port combinations. And we can also set some sort of other rules for various types of traffic, such as screen sharing, VNC, messaging traffic, IRC, and we basically have a few different buckets here we can choose from. We have default, higher, or lower. And so there's a default class, there's a high priority class, and there's a low priority class. So we could put our, latency sensitive traffic, such as, IRC and, maybe let's say DNS and ICMP and SNMP into our higher priority class. And then, we could lower some stuff if we wanted to as well. And that is the end of the traffic shaping wizard. At this point, you would click the finish button and it would generate a bunch of rules for you and generate a bunch of queues and then apply them and reload, and you would get dumped back into the overview view, which I will go back to. I'm not going to apply those since I've already done it. So once you've gone through the wizard, there's sort of two main parts that you're going to want to look at after that. So first of all, as I showed you before, you have the traffic shaper section, and this is where you can look at the individual queues that have been created. Now, like I said before, you're going to end up with a different result after you go through the wizard. And I've got a 3-tier queue here. So the way that you create a 3-tier queue, well, let me get to that in a second. So you have the queues here, and you can inspect them by clicking on them and change their limits and set service curves and stuff. And then you also have the rules, the firewall rules, and the WAN rules here are for inbound port mappings that I've set up. But there's going to be a bunch of floating rules that are created if you've chosen to prioritize or deprioritize game traffic or peer-to-peer traffic or other application traffic. It's going to create these floating rules for you here, and you can see under the queue menu here that each of these rules specifies a queue. And when two queues are specified, then one of them is the ACK queue and the other one is the sort of bulk queue. The idea with the ACK queue, or the acknowledgement queue, is that TCP uses lots of acknowledgement packets as a way to do flow control. And so an acknowledgement packet is just something that is sent from a receiver back to the sender that says, hey, I received that data, you can send me some more. So by making sure that these acknowledgement packets are always being transmitted and received with the lowest possible latency, then that allows the maximum usage of our resources. So we see all of our floating rules and we see all of our traffic shaping queues. Now, in order to create this 3-tier hierarchy, which is what you need to do speed boost, basically what you have to do is start in the WAN queue and then click this add new queue button, and that creates a new child queue. So if I do that now, I can give it a name like foo and a description like foo or whatever, and let's just say 1% of the available bandwidth. And then I save that, and I have to apply the changes for it to take effect. But you can see already that it's drawn over here as a child of the WAN queue and a sister of the queue SB up queue. So I can apply that change, and now I can grab this foo queue, and maybe I want to make another queue underneath of that. Well, you have to enable the queue first before you can do that. So you click save, or you click enable and you click save, and you might also get some little messages across the top here if there are problems with your configuration. So it's going to do a bunch of sort of pre-flight testing on your rules before they get loaded. The upshot of which is that it's pretty safe to hack around on this stuff, and it's actually pretty hard to break your network. I did all of this testing and bring up while it was actually in the critical path for everybody in the house. So pretty cool. So, and it's just telling me that I have the bandwidth stuff misconfigured, and I do. But now that I've added this queue and enabled it, rather, I can add another child queue, foo child. And, again, I can set, bandwidth or whatever. And if I save that, now you can see that I've got foo and foo child here. So I'm going to delete these queues. which should probably also delete its child queue, and it did, and I'll apply those changes. So in order to do the speed boost curve fitting, what you're going to need is a three-tier hierarchy, and you're going to want a root queue for the speed burst up and down, and you're going to want to configure each of those queues with a service curve that the values of which you're going to have to discover for yourself. And then you're going to put all of the child queues, which actually catch the traffic, underneath of that speed boost queue. And this is so that no matter what kind of traffic we have, it's all going to be funneled through that same service curve to make sure that the speed boost is applied for no matter what kind of traffic I have. And so we do that for the upstream and the downstream. So the way that I actually did this was to go through the wizard, and it created all these queues with these names. And then I created a new hierarchy of queues, and I basically made the queues exactly like the default queues, but I had a different name, like queue games new and queue others high new. So you duplicate all the queues, which is a bit of clicking that you have to do, and then in sort of one fell swoop, you just rename the queues and delete the old queues before committing the changes. So the point is, you want to make your new queues look like the old queues, but have them rooted underneath of the speed boost queue. And depending on your goals, you might not need to go for this three-tier hierarchy, but that's what I wanted to do. And this is still yelling at me because I forgot to acknowledge the error from before. So you come out with a three-tier queue, and that's great. Let me show you also some examples of my little sliding window doohickey. So these are using the terminal commands you saw previously. Oops. So this basically is a scrolling window showing network latency, and you can sort of have this going as you do tests. Let me acknowledge that. So for example, I'll do a speed test here, and let's get ifstat going too as well. So we can do some speed testing here. What the hell? There's all these decoy links that are like, oh, you want virus crap, don't you? No, I want to begin the test, yo. So the test begins. We see the downstream. Now it's 5:45 in the evening, so we're not going to be going entirely that crazy fast. But, we can see that, we had a bit more of a latency bump than we saw in the slides. But for the download, at least, the upload is clearly pretty flat. So maybe I can go back and tweak the downstream queue a bit more if I want to. But that just sort of gives you kind of a live demo of that. Let me also run pftop and look at the queue view by hitting the left arrow once. And this is going to show us in real time what the various queues are doing, and we'll sort of be able to make sure that we are in fact queuing both uploads and downloads. So I'm going to run another test, and we're going to be watching the queue length column here. So here's our downstream queue. In fact, we are queuing minimally on the downstream queue, and this time our latency cluster is quite good. Now the upload's going, and we see that we're queuing on the upstream queue as well. But not huge amounts of queues. These queues are all using the default size of 50 packets, which is reasonably low. Again, you want to try to refrain from queuing massive amounts of packets, because it is actually important to drop packets quickly if that's what needs to happen, if there's congestion. So that's a quick demo of some of the monitoring tools and how you can actually configure nested queues in order to do curve fitting for the Comcast Speed Boost. And that is the end of the screencast. Thank you for watching.